Unit 6, Chemical Reactions, Chapter 2, has us take a look at starting to take a look at the different types of chemical reactions. The different types of chemical reactions are going to be important, and some of them will be looking at predicting their outcomes. There are rules and guidelines that we have, and some of them are very straightforward on how they are to be predicted, and so we'll take a look at that as we continue through. Well, there's, for the most part, 5 basic chemical reactions. Combination or synthesis reactions is one. We also have decomposition reactions. That means you have one thing making a number of things. You have single replacement reactions, or also known as redox or redox reactions. And then within this, you have complete oxidation or burning of organic compounds. And everyone enjoys that one. And it will allow us to have some other things that are going on. Double replacement precipitation reactions, that should be very indicate that it's going to form precipitation reactions, meaning it will form a precipitate. Also, a lot of times that will be shorthand by PPT is for precipitate. A double replacement neutralization reaction, it usually has a little bit more difficult to determine their outcomes. You do have to look at and know what you have present in your chemical reaction when you are predicting these, because these ones are a little bit more difficult to predict. We will start in this units of notes or chapter of notes. We'll mainly focus on the combination or synthesis reactions, decomposition reactions, and single replacement or redox reactions. The single replacement reactions, we'll use a table on the back of our periodic tables that you should already have at this point. A combination or synthesis reaction has a general formula seen here as of A plus B gives us AB. Now the A and the B are just generalization of elements and or compounds and do not actually mean that A is a certain specific element or B is as in boron. These are just general formulas. I would highly suggest making sure that you are able to identify the general formulas, as that it will help you in your quest for predicting those specific outcomes. Combination or synthesis reactions, usually we're always going to have 2 things on the reactant side, 1 product, as that is you're combining or synthesizing something new. We will look at a couple of these simple ones. Some of them you might see in your everyday life, but we'll also continue with them with our balancing chemical reactions quest. When we look at the first one here, we see that hydrogen gas and oxygen gas come to form water vapor, or also known as water gas. And so what this happens is we see that it's not balanced. Our oxygen are not balanced on either side. And so by doing that, we'll make our little chart again, just like we have been, because I think it is very important to continue those types of things. It might be simple in that we only have 2 things, but it is important. Now, some might ask, why does hydrogen have a 2 there, and why does oxygen have a 2 there? That's because they are diatomic. Remember back earlier we talked about diatomics, in that when they they form in their pair or a molecule. We had to do those back in Unit 4 when we were putting together those molecular models. We looked at those when we were doing our naming, and so it's important that we also remember that that's why that is. So we have 2 and 2 and 2 and 1 oxygen. I need to balance out my oxygen. Well, by doing that, it is going to force my hand into also changing the number of hydrogen. Now, a lot of people would love to just put a subscript 2 by that oxygen. Well, that would be hydrogen peroxide. Not likely going to happen here. And so we now see that my oxygen are balanced, but my hydrogen are not. By putting a 2 in front of my hydrogen on my reactant side, I can see now that it actually isn't too bad, because they have things that are separated out. And that's going to want to be the things that we're going to be able to take and use to our advantage. The next one has us taking sulfur trioxide gas and then bubbling that through some liquid water to form sulfuric acid. So when I go and make my chart, I need to actually separate everything out. I need to have my sulfur, my oxygen separated, and my hydrogen separated out. SOH, so like geometry. Interesting. And so now we can see that we have sulfur is just 1, and it's also 1 on the other side. Oxygen, I have 3. And, oh, wait a second, caught myself. I don't have 3, I have 4. And I need to make sure that I have 3 here, 1 here. That will give me my 4 that I need. And now on the other side, I have 4, and it's easily seen. Hydrogen, I have 2 and 2. And lo and behold, I can see now that it's balanced. And that's just excellent. Now the next one is one that might be currently taking place on your car. Maybe not. Maybe you don't. Maybe it is. But we have iron reacting with oxygen gas to form iron 3 oxide, better known as rust or also hematite. When I go and do my counting, I have 1 iron on the reactant side, 2 on the product, 2 oxygen on the reactant side, and 3 on the product. Now this one might seem a little bit more difficult. We still do have to figure out how do I balance this. It's just going to take maybe a little bit of time. But now we can look at some things and it just allow us to, I would suggest, weighting to balance out the iron since it's by itself and on the other side. If I put a 2 in front of my iron 3 oxide, that changes my oxygen to 6, my iron to 4. Well, that means that I need to put a 3 in front of my oxygen on my reactant side to also give me 6. Now iron, all I need is a 4. And that makes my equation balanced. Now, why did I put a 2 in front of my iron 3 oxide? That's because the least common multiple between 2 and 3 is 6. And so I use that bit of information to allow my abilities to kind of work it through. And that's kind of be something that you need to see. If you see that you have an offset of 2 and 3, you're going to want to use that least common multiple and that little bit of math to your advantage. Now, decomposition reactions, well, they're opposite of synthesis reactions. Now, they do have some general types that we have, and a couple of them we will actually ask that you have memorized to predict their products. And if you look at the general formula, you have one thing on the reactant side making 2 distinctly different things on the product side. Now, there are 3 types of them. They are metal hydrogen carbonates, the decomposition of metal carbonates, which are usually just these 2 reactions are usually done in sequence. Kind of the product of the metal hydrogen carbonate becomes the reactant of the next one, but not always the case. Sometimes it can be. And then just the general decomposition reactions. Those ones don't have a nice hard and fast rule, so we'll have you just usually give a little bit more information on those into figuring out how we actually look at those. Now, the general chemical equations we have is that metal hydrogen carbonates decompose into the metal carbonate, water, gas, and carbon dioxide. Now, these are 2 things that they always will form, the water and the carbon dioxide, as long as it is a metal hydrogen carbonate. If it's something else, it's not always going to give us this water and carbon dioxide. The metal carbonate is the other thing. Now, which metal we use, that depends on which metal we have present on the metal hydrogen carbonate. For this first example, you can see that I used a calcium hydrogen carbonate decomposing into the calcium carbonate and water and carbon dioxide. Now this is a little bit different, and I could have used any metal that I have on the periodic table. I chose to use calcium because it balances out as we have it written, and so we didn't have to worry about balancing it out. I could have used iron 2 hydrogen carbonate. I could have used a zinc hydrogen carbonate. Now, some of these reactions are more likely than others, and so a calcium hydrogen carbonate might be a little bit more realistic when looking at the types of chemical reactions as opposed to maybe some of the others. Now, when we look at how this forms, we can see that water and carbon dioxide are there, and that I have a metal carbonate. I have my metal and calcium, and then I have my carbonate, it's CO3. Now in the next reaction, I can see that I have a metal carbonate, that is my calcium, and then a carbonate ion there. My metal oxide is my calcium oxide in this case, and carbon dioxide. Now some people might wonder, why is there not water present? Well, water can't be present as a product because on the reactant side, I do not have any hydrogen present. If hydrogen isn't present as a reactant, there's no possibility that water can be even a product. So you have to follow the rules that we set forth in Chapter 1 in the Law of Conservation of Mass. Meaning if it's not there, we can't make it just because we want to. No general formula is given for the third type, but usually you're going to be given those ones to you. So let's look at some. So here I have sodium hydrogen carbonate decomposing to make a metal carbonate. And now I still have two products that I need to come up with. One of them should be water, and the other one should be carbon dioxide. Now that usually would be a water gas, and carbon dioxide is also usually always found as a gas. Why is that shown as aqueous is beyond me. That should always be seen as a solid. That is a major typographical error. That is very naughty. Now, when this happens, we actually see this, and this is kind of why we put baking soda on a grease fire, as that baking soda, also known as sodium hydrogen carbonate, will decompose to make sodium carbonate, water, which is a very little amount actually, and carbon dioxide, which we know will smother most fires, or is not going to be a fuel for the fire. Now the water that's present, and why we don't do this, is putting water on a grease fire. Grease fires are usually going to burn a little bit hotter, and actually will allow that water to decompose. Very little water is actually produced in this reaction that would allow for that fireball to actually happen, because when you have the decomposition of water, you're actually going to decompose it into its elements: hydrogen, a combustible fuel, and oxygen, fuel for a fire. So what you have here is a sodium carbonate solid, helps smother it, and more carbon dioxide. Now if we look in our next example here, we see that that sodium carbonate can be further broken down into a sodium oxide, something that we also see as just a smothering unit, and just an inert solid. And another product will be carbon dioxide. Now carbon dioxide is going to again help the smothering process in making sure that it does not allow for the fire to continue. Now this is, again, why baking soda is suggested for grease fires. Now this is also why we use baking soda in our cooking, because baking soda, sodium hydrogen carbonate, will produce carbon dioxide. That will allow the breads or the muffins that is used to actually rise. It gives it that nice airy look to it. And it continues to further decompose into a sodium oxide and more carbon dioxide, making the muffin nice and light and fluffy. But when I look at my first one, it's not balanced. What was I doing? Well, I was just getting ahead of myself and getting all excited about the chemistry on why we do some of the things that we do. And so we see that I need to have a sodium, I need hydrogen. Now my carbonate is split up on the other side, so I have to split it up into its elements, which might seem like a very daunting task, but it might end up being an okay thing, ultimately, in the end. And so I have one sodium on the reactant side, 2, and then I have hydrogen, and then I have 2 hydrogen on the product side. Carbon is 1, and then I have 2, and it's important that I see 1, 2 for that. And oxygen I have 3, and the oxygen on the product side I have 6. I go 3 plus 1 is 4, plus 2 is 6. And so when we need to balance that. I can see that everything on my reactant side requires me to put a 2 in front of it, and therefore it will be completely balanced, as I can see 2, 2, 2, and 6 as we balance that out. Now in the next example, I can actually see that it's already balanced, that I have 2 sodium on both sides. I see that I have a carbon on both sides. I have 3 oxygen also spread out on the product side between a 1 and a 2. So no further balancing is required. More examples of a decomposition of a metal hydrogen carbonate. We can see here that I have an iron hydrogen carbonate, and an iron carbonate is being produced. Now what do I have to do with that is I still have 2 products that need to be made. The 2 products that are always going to be present on the product side of a metal hydrogen carbonate decomposing are, one is carbon dioxide, and the other is water. And see, I can see that these things do work, and it doesn't matter which one I wrote first. If you would have said water first, I would have written water first, or carbon dioxide. It doesn't actually matter where they are in the reaction. But I can see that my reaction is not balanced, and therefore I need to go through and write out my little chart here, and I can see that I have to split up my carbonate and do my accounting of that. I have 1 iron, and then I have 2, and then I have 3 hydrogen. And we can see that it's a little bit difficult, but it is 3 because I have to distribute that 3 to everything that's inside there. That means that I will also have 3 carbon, but now 3 times 3 is 9 oxygen. And now the hydrogen on the product side, I see that I have 2. And then I have carbon, I will have 3 plus 1 is 4. And my oxygen, I now have 9 plus 2 is 11, plus 1 is 12. Now I'm going to want to be very careful on how I balance this one, because by balancing changing anything on the reactant side is going to have an effect on what I have on the product side. But I know I'm going to have to balance out my iron first, and that's the big one that I need to worry about. And so I'm going to put a 2 in front of my iron 3 hydrogen carbonate. I need to now change and double everything on my product side by 2. Or just double it, actually. And so now, but hydrogen's only in one place on my product side, so all I have to do to balance that out is put a 3 in front of it. And so that goes there. Now, to balance out my carbon, it gets a little bit more tricky. But I can see I don't want to do anything to this iron carbonate. I have 3 of them. Well, if I put a 3 in front of this carbon, 3 times 1 is actually 3. And so then I would actually have 3 plus 3, which would give me 6. Now let's take a look at my oxygen, because I've been dealing a lot with this other stuff that I haven't dealt with oxygen yet. And so I have 9 still here. So I have 9 plus 6, which is 15, plus 3, which will give me my 18. And so it happens to be that oxygen just balanced itself out. Now in the next example, we can see that I don't have hydrogen present, so one of the products cannot be water. So when I look at this, I need to make sure again what would be my other present. Now some people might want to just put in carbon and make life easy. Well, it's not always that way. And so we need to actually have carbon dioxide as the product. And so that would actually be a solid present, and that would be seen as a gas. And so I can see here I got a iron and iron is balanced there, and we'll write it all out because I have a sneaking suspicion that this is not going to be balanced. And so iron 2 and 2, carbon is 3 and 1. Oh, look at there. And oxygen I have 9. And on the product side I have 3 plus 2, which would be 5. I need to make sure that I now have 3 carbon on the product side. So by doing that, I'm going to put a 3 in front of my carbon dioxide. But that changes my oxygen as well to saying 3 plus 6, 3 times 2 gives me 9. Now on the last one here, we have just a general decomposition reaction. Might be a little bit difficult to actually do the predicting of. So when we do this, what we have is that we have the chromium. We still do our normal chart, just like always. So we can see what is going to be present. And I do my chromium. And I do 3 nitrogen and oxygen, 1, 3, and 9. Now on the product side, I have chromium is 1, my nitrogen is 3 still. Well, isn't that just nice? And I now have oxygen at 6 plus 2 is 8. Now, we have to use one of our little tactics here that we can use to our advantage is what times 2 would actually give me 9, or allow me to have 9. Well, 1.5 would actually work, because then we would have 3 on that side there. But I can't use 1.5. But what I can do, and that's interesting, is that I can double everything. If I double a half, so if I had a 1.5, that would balance it out. But I can't do that. But what I can do is I can double everything, and so I have a 2, 2, and then a 3. It's a little tactic that we can use to our advantage. I can double check this now, and I see that I have 2 chromium, and 2 chromium on the product side. Nitrogen, 2 times 3 is 6, therefore I have 6. 9 times 2 is 18, and now I see that my nitrogen is also still balanced out. The oxygen, 2 times 3 times 2, well, 6 times 2 is 12, plus 6 is 18. And it balanced out. Yay! That's what we want. Balance the following equation and indicate whether it represents a combustion, combination, or decomposition reaction. Single replacement reactions involve a metal usually replacing another metal in the solution. As we can see, the M is a generic metal, N is another generic metal, and X is an anion. And in this reaction, M is going to replace N in this reaction. Now how this actually works is a little bit more involved than we might want to deal with, and so we won't be looking at that. And so we're going to look at maybe more of a generalization and making some of these predictions, because there are some reactions in this case that will not actually happen, and so we need to be very careful. But it has that one thing replacing the other. Now, nonmetals can replace nonmetals, but it's usually only seen with the halides, is that one halide would replace another halide. So in the lab, I know this is one that is commonly done. You place an iron hook or an iron staple in a solution of copper 2 sulfate, usually a pentahydrate, and the hook starts to turn dark, and over time it starts to even look kind of rusty-ish, and it looks like it's grown bigger. Well, what's actually happening here is that iron hook, in this case, will be our solid and reacting with the copper sulfate. Well, what's happening is that iron is coming out of the solid and becoming a solution, and what's being replaced as a solid then is the copper, and that's actually what's forming on that iron hook or iron staple, is that the copper is coming out of solution and growing on that metal that was originally there. Eventually, that metal would completely go away, and through that time, the only thing that would be left would be the copper metal. You should actually be doing this in the lab at some point in time. Now, the reverse does not happen. Copper will not be replaced by iron in a solution. Now, which ones work and which ones don't is found. Now, sometimes we write out no reactions as NR, and sometimes I will write them out as no RXN as a means to showing no reaction, and that's how I usually will write shorthand writing in that. So how do we know? Well, we use something that's called the activity series. It's the way to figure out which one is going to replace another one. Now, hydrogen's not a metal, but is included in this because a lot of times these metals will form and or react with acids. Not all of them will, but which ones they do are sometimes important. Understanding which metals will react with which acid is something that I feel can be better explained or seen in the lab, and so that you can experience some of that. What we look at this reaction or this activity series is kind of like a popularity chart, is how I usually view it. Now, this might be a little sadistic, but it is how it is. And if we look at it as a popularity chart, that lithium is one of the most popular metals. It is more popular than calcium and aluminum and so on and so forth. Well, if you go and look at which metals are near the bottom, these are ones that you actually can find as their natural, stable state, and they will be seen in the real world. You can go and find silver, not as likely as you used to, but copper and silver and gold are near the bottom of the activity series. They don't have to form compounds. Lithium is highly reactive and always forms a compound. Therefore, I always say it requires a friend. And so iron might not always be popular, but it will form a friend in certain circumstances. But see, if we look at our previous example, iron likes to have a friend more than copper does, and therefore copper got replaced by iron. So the sulfate was going to the more popular metal. And that's kind of how we look at it, is which one is going to be replaced? Well, which one is higher? And if you have something that is in a solution having an anion that's high on the popularity chart, and the thing trying to replace it is lower, it's not going to happen, so no reaction will actually happen. Whereas if you say you have a sodium metal by itself and a lead solution, sodium is going to react with that solution and kick lead out, so to speak, and it will no longer have its friend. Again, it's a little sadistic, but it does work, and as you kind of look at it as a popularity chart. Who needs the friend? So let's do some predicting. Here we see that sodium and potassium chloride are in a solution or in a reaction. Now, which one is more higher up on the activity series? Well, if you have to look at the back of your periodic table, and you will see that potassium is near just a little bit above sodium. Now, chances are this reaction would still kind of happen. It's just going to be actually sodium reacting with the water that's in the solution and not actually replacing it with the potassium, and you're not going to get it precipitating that out. So then because of that, you're actually going to see no reaction in this case. Now, magnesium is much higher on the activity series than zinc is, and therefore zinc is going to come out of solution and form a solid. Now, magnesium is going to form a compound with the nitrate. Now, this 2 on zinc came from zinc, on the zinc nitrate came from zinc. So we have to kind of look at, okay, what is the charge of magnesium? In this case, it's also a positive 2. And so when we do our reaction, we can see that magnesium nitrate is also going to have the parentheses with the 2 on the outside. The 2 does not necessarily always stay with it. It all depends on the charges that you have, such as the case in this next one. You have lithium, and which is the most popular activity series. So that's the James Dean of his day, so to speak. He's the cat's meow. Everybody wants to be friends with lithium, and so sulfate is going to leave gold away. Now, some of you might think, but I want to be gold's friend because gold's expensive. Yes, you might be correct in that, but when it comes to activity series, it's all about who's higher up on that. And so the sulfate is no longer going to hang out with gold, and gold will be by itself and will be precipitated out in a solid. That 2 that's on gold, it doesn't stay there anymore because that came from the sulfate, and now the lithium has a positive 1 charge, but because sulfate has a negative 2 charge, it gets a 2 on the crisscross, and then you will see that you have your sulfate. Now in the next one, you might be a little bit tough to find cobalt on the activity series, but it's there, and it is higher than lead on the activity series, and therefore in this one we have no reaction. Now, which one's a group of metals and more reactive than the rest? And these are the active metals. These ones will react with water very quickly and violently in some cases. Lithium, potassium, barium, strontium, calcium, and sodium will react with water on contact. And we saw this when we looked at our activity series or reactivity going down a group. And we saw that with that. And so we have these active metals present in the reactions. In the next chapter, we will be continuing our look at chemical reactions. We will start combustion and double replacement reactions.